The profound impact of AI on contemporary engineering design is explored in this video. Viewers will be given a deep dive into how artificial intelligence is shaping the future of innovation and problem-solving within the engineering field. What if the next skyscraper was designed by an AI? Or a bridge that self-repairs with no human intervention? We're not talking science fiction anymore. Dive into the incredible ways artificial intelligence is not just assisting, but fundamentally transforming modern engineering design, solving problems we never thought possible and shaping the future of innovation. Struggling with complex engineering challenges, or feeling like innovation has hit a wall? The answer might surprise you: AI. This video reveals how artificial intelligence is becoming the ultimate co-pilot for engineers, designing solutions faster, more efficiently, and with capabilities that humans alone simply can't match. Discover how AI is literally building the future. Imagine a world where machines aren't just built, but intelligently conceived and optimized by other machines. That future is here, right now, within engineering. Join us as we explore the profound impact of AI on design, pushing the boundaries of what's possible and revealing how artificial intelligence is rapidly becoming the most powerful tool in the engineer's arsenal. AI has evolved from a tool for automating tasks to a creative partner for engineers. This is enabled by techniques such as generative AI, which can create thousands of design options based on specified criteria. Aerospace, generative design has been used to create lighter, stronger parts, such as a seat bracket for General Motors that was 40% lighter and 20% stronger than its human-designed counterpart. Architecture, AI assists with site analysis, energy efficiency, and creating complex geometric forms. AI is accelerating the discovery and development of novel materials with enhanced properties, a process that was once slow and resource-intensive. Property prediction, machine learning algorithms can predict the properties of a material, like its thermal conductivity or melting point, based on its composition and structure. Inverse design, instead of testing existing materials, AI can perform inverse design, where it is given desired properties and identifies the material compositions that would best achieve them. Additive manufacturing, AI optimizes material and production processes for 3D printing, enabling the creation of custom-designed, high-performance parts. Increased efficiency, AI automates repetitive tasks, freeing engineers to focus on higher-level problem-solving, innovation, and creativity. In an engineering context, AI is a suite of technologies that allow systems to learn from data, reason, and create innovative solutions, going far beyond simple automation. AI enables systems to simulate human-like intelligence for complex problem-solving and optimization across different engineering disciplines. Predictive maintenance, AI analyzes sensor data from industrial equipment to predict failures before they happen, moving maintenance from a fixed schedule to a just-in-time approach. Machine learning, ML. This core concept uses algorithms and statistical models that learn and improve performance over time through experience. ML is applied to tasks like quality control, where AI systems can automatically detect defects with higher accuracy than human inspectors. The convergence of powerful computing, vast data, and advanced algorithms has brought about a pivotal moment by creating the necessary conditions for the latest wave of artificial intelligence, AI, particularly large-scale models like generative AI. The synergy between these three elements allows for breakthroughs and efficiencies that were previously impossible, creating transformative changes across numerous industries. Powerful computing, this refers to the exponential increase in processing power over recent decades, driven by innovations in hardware. It includes high-performance computing, HPC, which networks servers into clusters for complex calculations, as well as specialized processors like graphics processing units, GPUs, and tensor processing units, TPUs, that are optimized for parallel processing. Generative design uses artificial intelligence, AI, and machine learning algorithms to rapidly explore millions of design options based on a set of performance goals and constraints defined by an engineer. This process allows for the creation of optimal, efficient, and innovative solutions that human designers might not uncover through traditional, manual iteration. Define parameters. An engineer first specifies the high-level objectives, such as minimizing weight or maximizing strength, and the practical constraints, such as available materials, manufacturing methods, and maximum stress. Generate solutions, AI algorithms, like those based on neural networks or genetic algorithms, then generate a multitude of designs that meet these specific criteria. Unlike traditional computer-aided design, CAD, the AI does not start with an existing model. Instead, it creates the model from scratch, using algorithms to learn and refine its solutions. AI uses predictive modeling and simulation to accurately forecast material performance and system behavior, significantly reducing the need for costly and time-consuming physical prototyping. By learning from vast datasets of existing materials and simulation results, AI can predict how new designs or material compositions will behave under different real-world conditions. Rather than relying on manual trial and error, AI can generate new materials based on a desired set of properties. Process AI models, including generative adversarial networks, GANs, are trained on databases containing the properties and structures of known materials. The AI learns the complex relationships between a material's chemical composition, crystal structure, and performance result. Engineers can specify performance requirements, such as superior strength, conductivity, or durability, and the AI will suggest novel compositions or microstructures to meet those goals. Automated feature detection and anomaly identification is an AI process where algorithms analyze complex datasets to recognize normal patterns and flag deviations, which could indicate critical design flaws, system failures, or security threats. This technology learns what is normal and then identifies outliers, leading to proactive problem-solving in various fields like cybersecurity, finance, and manufacturing. Common techniques include deep learning models like autoencoders and unsupervised learning to detect deviations when labeled anomaly data is scarce. Learning normal patterns, AI models are trained on large datasets to establish a baseline of expected behavior or normal patterns within the data. Identifying deviations. Once the normal baseline is established, the AI system flags any data points, patterns, or events that significantly differ from this norm. Deep learning. Architectures like autoencoders learn compressed representations of normal data and flag reconstruction errors as anomalies. Unsupervised learning, used when labeled anomaly data is limited. These methods, like one-class classification, identify anomalies without prior labels by grouping data points. Time series models. Specialized architectures such as LSTMs and transformers are used to capture temporal dependencies in sequential data, which is common in anomaly detection. The engineer of tomorrow must upskill and reskill to integrate technical prowess with AI-specific knowledge, data literacy, and human-centric soft skills. While AI can automate repetitive tasks, it creates new opportunities for engineers to innovate, solve complex problems, and add strategic value. A mindset of continuous learning is essential to keep pace with rapid technological change. Programming. Proficiency in languages like Python is fundamental, along with familiarity with others like Java, C++, and R for specialized applications. Engineers should also be skilled with version control tools like Git. Machine learning, ML, and deep learning, DL engineers need to understand the principles of ML algorithms, e.g. supervised, unsupervised, reinforcement learning, and deep learning models, e.g. neural networks. AI frameworks and platforms. Expertise with industry-standard tools like TensorFlow and PyTorch for developing and deploying AI models is vital. Cloud-based platforms such as AWS SageMaker and Microsoft Azure AI are also becoming essential. DevOps and MLOps. As AI models move into production, engineers need skills in deployment, automation, monitoring, and pipeline management to ensure models perform consistently in real-world applications. Creativity and innovation. With repetitive tasks automated, engineers can focus on creative, high-level design and innovation, using AI as a tool to explore new possibilities, as seen in generative design. Ethical decision-making and bias awareness. Engineers need a strong understanding of responsible AI principles, including fairness, transparency, and accountability. This is critical for preventing bias in models and mitigating risks associated with AI-driven decisions. Navigating the responsibilities of bias, accountability, and societal impact in AI-driven design requires proactive measures to ensure fairness and equity. This involves using diverse, representative datasets to mitigate bias, establishing clear frameworks for accountability across stakeholders to prevent discriminatory outcomes, and understanding the broader social effects of AI, such as job displacement and economic inequality, to promote ethical integration and trust. AI is reshaping engineering through the rise of self-designing and self-optimizing autonomous systems that use continuous learning, generative design, and agentic AI. These systems will streamline workflows, improve efficiency, and enable new forms of human-AI collaboration. AI will become a fundamental tool in all engineering disciplines, such as mechanical, civil, aerospace, and biomedical. Applications include using AI to predict structural degradation in bridges. Integration with the Internet of Things, IoT, and digital twins. AI will be combined with IoT sensors and digital twins, virtual replicas of physical systems, to enable real-time monitoring and advanced simulations. This will provide deeper insights into system performance and lifecycle management. Advancements in computational power. The future of AI relies on hardware innovations, including quantum computing and new GPU technologies, which will provide the processing power needed for more sophisticated AI algorithms. Research into alternative architectures, like matrix long short-term memory, MLSTM, is also focusing on creating more efficient and faster AI systems. The next step in autonomous systems is for them to become truly self-designing and self-optimizing, with the ability to dynamically adapt to complex and changing conditions without constant human input. AI-driven material discovery accelerates the creation of novel materials with bespoke properties by replacing the traditional, slow, and expensive trial and error process with data-driven methodologies. By leveraging vast datasets and advanced algorithms, AI helps scientists screen potential materials, predict their performance, and generate new material candidates with unprecedented speed and accuracy. This revolution is crucial for developing advanced materials for next-generation technologies like renewable energy, sustainable manufacturing, and semiconductors. Databases. AI models are trained on large, well-curated material databases, such as the Materials Project and Open Quantum Materials Database, which contain information on the properties, composition, and structure of known materials. Representation. Instead of using human-crafted descriptors, advanced AI models use techniques like graph neural networks. Predictive modeling. Machine learning algorithms and deep neural networks are trained on materials data to predict properties like thermal conductivity, mechanical strength, and electronic band gaps with high accuracy. High-throughput virtual screening. AI can rapidly screen millions of potential material candidates based on desired properties, eliminating most possibilities without conducting costly and time-consuming physical experiments. Reduced computations. AI models can be trained on computationally intensive simulations, like density functional theory, DFT, to learn the underlying physics and predict material behavior for new compounds at a fraction of the original computational cost. AI enhances global engineering projects and knowledge exchange by automating complex tasks, enabling real-time collaboration, and creating a unified, data-driven environment. It overcomes traditional hurdles like geographic distance, language barriers, and data silos, ultimately leading to greater efficiency, innovation, and stronger interorganizational relationships. Accelerated design cycles. AI-powered generative design allows engineers to input design goals and constraints, and the AI rapidly generates thousands of optimized design options. This speeds up the development process and produces innovative, high-performance solutions. Virtual prototyping. AI-driven simulations and digital twins create virtual replicas of physical assets, allowing for real-time monitoring and optimization. This reduces the need for expensive physical prototypes and provides more accurate performance. Targeted training. AI identifies skill gaps and uses individual learning data to create personalized training programs. This ensures employees stay current with industry advancements, increasing their value in a rapidly evolving field. Self-service knowledge portals. AI-powered portals allow employees to access information and receive tailored recommendations based on their roles and projects. This fosters a culture of continuous learning and reduces the time required for new employee onboarding. Sentiment analysis. AI analyzes the tone and sentiment of team communications to gauge morale and detect potential issues, enabling managers to address problems in global teams before they escalate. Enhanced communication. AI-powered chatbots and virtual assistants provide quick answers to queries and automatically summarize meeting notes. This facilitates smoother communication and reduces administrative load.